this tutorial is interactive. So there are a lot of places up here where you can sit with your laptop if you're interested in that. In a sense, I hope you will open a Colab notebook during this presentation. Are you warned? So I'm here to talk about multi-arm bandits in the wild. And originally, when I sent in the proposal, the idea was that people who wanted to go to consequences but didn't know enough, they would go to my tutorial and then I would kind of prep them for consequences. So if you're here and you were at consequences and you understood everything, then then I don't know if you maybe should go and use your time elsewhere. If not, then stay and listen. My name is Falk. If you don't know me, I have been in industry since 2003. I started out I have a master's in computer science. Then I worked 10 years while there was no machine learning, nobody who believed in any of those kind of things. And then by chance, I ended up in a company that worked with recommender systems. And since then, it was basically love at first sight. And I've been working with those ones since then. I wrote a book called Practical Recommender Systems. I'm writing another one. In RecSys, I've been industry chair twice, and I was sponsorship chair this year. In my spare time, so to speak, I'm a principal recommender engineer at a company called DPG. If you're not from Belgium or the Netherlands, maybe you don't know it. It's quite a big company where we work with news and video on demand, kind of Dutch Netflix type of things. Lots of interesting problems. I think I already mentioned that I assume that you're here because you want to learn about bandits. If you're an expert already, as I said, you're more than welcome, and then you can help answering questions afterwards. But it is an introduction. So my goal is that when you finish with this tutorial, that you have kind of an intuition about what it is and how you can apply it in work. And then in that, I will also share my personal experience on working with them in industry. I'm a little bit unsure about how long it takes, but I will say I have around 2 hours. Maybe it will be longer, maybe it will be shorter. A dear friend of mine took this picture of me while I was stressed working on another presentation. This was mostly just to remember everything. So this is the first task for the audience. Could you use that QR code and then see if you can get into the Google Doc? No, that didn't work. Okay. So the idea is that that you should find a document like this. It is simply because I didn't know how to fast or quickly put up a Slack group or something like that. So if there is an exercise later, and then we can share details through this Google Doc. And then the intro. So why do we want bandits? And the way that I think, kind of a funny way of looking at it, is that we always talk about user-centric recommender systems and so on. But bandits is also, of course, they want to make, we add bandits to make better personalization and so on. But actually, if we could just optimize it for the bandits or the robots to learn more about what they actually should do, then I believe that we should, then you'll end up actually making both worlds better, or the user worlds better. I don't know about the bandits. So I don't know if you could call it bandit-centric learning. Most banding algorithms, the 3 algorithms that I'm going to show you today, I can put them on one slide and they're very easy to go through, but don't be deceived because there are so many ways that you can get into trouble. And just a few examples on where I have and I'm planning to use in the future some bandits. For example, if you have a video on demand kind of platform, the banners, you can use those ones. If you want to choose them or personalize them, then a bandit is very good. Another place you can do it is also if you have several slates or rows, then you can also use a bandit to decide on that one. And then pushing it also, if you have a rather small catalog, you can also use it to select the best choices here. Again, we also have news at DPG, so you can also use Bandits for news. In fact, news is a great place for using Bandits because often you have new content that you don't have a lot of history on, and then that way you get a fast feedback loop. This was just a few of the examples, so I thought I'll come back to them later. So since this is called multi-arm bandits at a RecSys conference, I just thought, why is it that we actually need to have recommender systems with uncertainty? Because can we just predict everything? And then I'm going to use some of the slides I used Monday at the RecSys challenge. I hope some of you were there. I'm sorry to reuse them. So basically the job of a recommender system is to find content for users, right? Often the recommendations that we actually end up showing are very similar because if somebody has bought a cup, then it's very easy to recommend other cups. But what we want to do is actually to show a large different selection of content, but we don't really know enough about the users often. So what does it actually mean when we talk about doing recommenders? And again, we just rank list of content. It's not that we can generate recommendations because we can't do that yet. Or well, it depends on who you ask. Some say we can do that soon, but so far no. And then the last question to ask is that if it's just about re-ranking list of content, is there then one optimal one? And of course, no, there isn't. And here is then you can discuss whether this is correct with search. But usually you don't have just one list that is correct, because I'm sure that Morten down there would re-rank his recommendations different than me, and so on. So one of the things that you should consider is that it always depends on use cases. And I think that, so there are many things that you can discuss what a user is doing on a website and why they need recommendations, but mostly that, often they come because they have some specific need right now, which is very hard to predict. But we also want to give them a chance to discover new stuff and educate them on the new content. But always remembering to recommend the current use case. And so if we don't really know the use case, and then on top of that, we have this problem that people love to talk about the ground truth of data, but usually we don't really know enough about the user and our catalog to actually, be able to do a good prediction. Exactly because if a user knew all the catalog, then we probably didn't need to give them recommendations. And so, no really ground truth. So we have all these kind of uncertainties that we can then say, is it then really relevant to talk about a prediction, really? When actually, I think that the best thing we can do is that we can just look at the distributions of each content item of the user and then say, we should try and sample for that. And that's where Bandits are very good. And just to talk about where we can find these things interesting, at least from an industry point of view, is that when you have your research workflow, you have some data, you implement an algorithm, you optimize the test data, and then you make a report. And then the discussion is, of course, if it works. So you can discuss many places, and we have done that for a week now, discuss how you evaluate it correctly and so on. But what we will start out talking is somewhat to the left here, where we're talking about A/B test and explore and exploit. And then later we will go back to kind of push it a little bit further back. Since I'm talking about doing things in the wild, then I have my favorite boss here, and he says that we don't really need offline evaluation, so we can just push it all to production. And then he says, well, we don't even need, how about we just push everything and then just fix it fast in production? And then, of course, no, we shouldn't do that. So one of the last lines of defense before we throw something to the grand audience of everybody is that we use randomized control test, or also known as A/B test. This is a good place to set the stage for Bandits. I'm not going to talk about how you do A/B tests, Bandits with A/B tests. It's just to set the stage. So please don't leave yet. So basically, when you create an A/B test, you just split it into two groups. Remember the randomization, it can be quite tricky. I learned that many times, but without going into too much detail. So basically, an A/B test goes like you have your users, you have some kind of element that makes the experiment controller, which will then decide who should see what. And then at some point, you will have a chart like this, hopefully, and say B was better, and then everybody's happy, right? Usually, though, B is maybe not better. Usually, there are some kind of segments that are not actually happy with everything, and so you're just, if you think about it, you just did an A/B test, and you waited for so long, and then you discover, well, B was better, but then I just wasted a lot of time and a lot of users on A. And this is where we then start thinking about introducing multi-arm bandits. Because, for example, if you're recommending something different in movies and you are actually recommending animals instead, sorry, not recommending animals, if you're doing drug tests on animals, then it's good that we get it tested well. But there was a guy many years ago in the 30s, and he actually came up with this concept because he didn't want the mice to suffer so much. Of course, they also wanted to test it on humans, and then the next guy who came up with it, he then used the term one-arm bandit and then two-arm bandits. And as far as I understand, there was actually a machine where you could choose between which arm you would do. And basically, the whole question of multi-arm bandit boils down to, if you have a choice and you don't know which one of them is the best, which one should you then choose next? Which is what I said here. So in a sense, you have two arms, you want something on the left one. Do you then think that the left one would be the better one to continue with, or the right one is just waiting to warm up to give you 100 money or something like that? And so the discussion is always, should I exploit what I know now, or should I then try and explore? A different way to think about it is, you could think about whether we should go to the usual Friday cafe, or we should try something new. There is tradition, but it could also be just a local maximum, and actually there was a place just around the corner that would be much better. And so the question is, how safe are you exploiting what you know right now, and how much would you gain if you then explore for the future? And the thing is that with recommender systems, you're always focused on how the next click, the next recommendation, I want to gain the next click. But the problem is actually, it might be that it's worth learning something. I'm not telling you to go to school, but it's worth kind of going back and then try out different things, and then in the long run, you'll actually gain or this one is clicking faster than me. In that way, you will then gain long term. That's what I was saying. The terminology, just to get it right, is that this thing that I'm talking about that chooses an action, this is what you call a policy, for example. In an A/B test, you can then say that that's a random policy. It's 100% explore. So, but then what is actually the performance of a bandit? And you will read a lot of papers that talks about regret. And regret actually means that if you knew the perfect thing to show to everybody in your recommendations, then how much would you regret exploring things right now? So if you can do the maximum or the best thing all the time, exploit what you know, then maybe that would be the right one. But otherwise, you then, I say, it's always a bit the mystery to me, in a sense that as soon as I start philosophizing about it, it gets confused. But so don't worry if you're confused too. The problem is that in production, you don't know what's the best, in the sense that you can say that your usual CTR is something like 4% or 3%, and then you can look at the regret that way, but usually it's just your CTR, you look at it. But so back to this A/B test that we have. We have an A/B test that runs for a while, where we, in theory, we get lots of reward, and then we get lots of regret. At least that's how we work it. But the question is that most people don't actually think about what is it that I'm losing or what's the cost of doing an A/B test, because they believe that you just keep winning on it afterwards. But it's an interesting concept, because if you're always doing A/B tests, that means that a percentage of your traffic is always suboptimal. And then do you actually get the extra reward for doing suboptimal treatments or variants? So it's important that you consider your horizon when you think about what is my experiment, because should I go to the university because I get a better salary the next 20 years, or should I put this new model that I don't know if it's working into an A/B test or not? And so one of the ways of looking at bandits is also how can I actually reduce this regret as much as possible and still, gain and reducing. And then you can say, okay, so I'm saying, why do A/B tests if you can do bandits? And then people usually come and tell you that, well, if you don't do the correct number of data points, then you risk that you have false positives. Which is also correct. There is a bandit that I'll show a little bit later that then takes care of this. But it's not that, so the thing that is interesting is also that A/B test nowadays is that, well, we did an A/B test, so we know that this is better, but actually you don't. You just say that you're probably not wrong if you put this into production. And the way that the equations are put actually ends up saying that there is an adversity towards not moving things. So you have to have your p-value that is under 5%, so that means that you only risk, there is a little risk that you have the wrong choice, but on the other hand, it's much higher, the false negative problem. That's also worth thinking about. So if we could reduce the test on animals, or if we could let us suffer less on YouTube or the things we watch. So 20 minutes into the presentation, now let's talk about the multi-arm bandits environment. And basically, does anybody not know what a bandit is? Show of hands, favorite, some? No, he just took a picture, okay. Awesome. So just to go through it anyway, we have the environment, this is the world. The agent is the software that contains the policy. At some point in the life, there is a context that arrives and a number of available arms. It's important that you think about the available arms, because even if it's a bandit, it's not always the same arms that you have available to show to this user or in this context. Then there is an arm selection, and then hopefully there is a reward. The context shows the current situation, and the context is always something fluffy in the sense that people talk a lot about what's the context, and most people mean different things. Here I'm just saying that it could be the user or time or something like that. Other thing that is important is that you consider that a policy is something stochastic, that usually it can be sampled, and most of the available arms will have a small chance to actually be shown. So the goal of this bandit is again to maximize payoff. And it's important to notice that if you have 10 different arms, then it's actually only one of the arms that you'll get some feedback on, which is also something that doesn't seem very important, but it is. And then you should remember how many trials do you have. In a sense, if you calculate how much time or how much reward you want or how much CTI you want, then think about the horizon that you're doing. And I'm laughing because maybe it says in the slide, Morten will help me draw some distributions here. I'm sorry, Morten didn't have time, or I didn't ask, but so we are supposed to. So basically the problem with the bandit is it's not so much, we think about it as it should choose the correct thing, But what you should consider instead is that each arm, and we can think about the casino example here, has a different distribution. And we're trying to understand what's that distribution more than actually figuring out what to do right now. So it's a learning problem more than prediction. And again, we can take an example and show, okay, so if this is me, I'm watching streams, DPG Media, I open one of our video-on-demand websites. Context is me opening it from my cellular phone, maybe. DPG shows me a banner, and maybe I click on it and I go to a reward. Often you talk about simulations and playgrounds because otherwise it becomes difficult. And so the bandit problem often is when you talk about it in research is that you say, I actually know the distribution of what these arms are. And then a way to prove that the bandit works is that it can then figure it out from what it's doing. So basically it should learn the hidden distributions. One of the funny arguments that you can then discuss with people is that even if there is kind of a fight all the time about what's an A/B test and what's a multi-arm bandit, then you can actually look at an A/B test as a multi-arm bandit also that is called explore and then commit bandit. And this is kind of my introduction overall, the philosophy, the idea behind it. And then I'll spend some time introducing 3 popular bandits. It's 2 dogs and a cat. No, they're called the E-greedy, the Thompson handling, and then upper confident bound bandit. And they, of course, they are trying to do the same thing, but there are different ideas behind it. The epsilon-greedy should actually be called the epsilon-1 minus epsilon-greedy, because it's greedy epsilon minus 1 times when it gets called, and then, so basically what you can say is that if you throw a dice, a 100-sided dice, and it becomes 99, it will say, I'll show you something random, otherwise it will just show you the one that is the best one. It's very simple. So this is the first code. If you can implement this, then you have implemented a bandit. Congratulations. Then there is a lot of fun around how you actually do that in a good way. And this is where I'm going to try and open my notebook and then quickly go through some code. And I have to say that it worked on my laptop in my hotel room, and I hope it also works here. Does anybody have any questions at the time? It's a tutorial. We're supposed to discuss things. Nope. Can I then show of hands, is it because you have no clue what I'm talking about, or is it because everything is crystal clear? So who says you have no clue? All right. And who thinks it's all crystal clear? Okay, good. Just wanted to be sure that it wasn't like everybody was afraid of saying anything. It might feel like I went through it a lot of times, but from my industrial experience, I have discovered that people assume that they know, and then they don't talk about it more, and then it turns out that the assumptions that people have are different. And then they go out and work on the same thing they think, and then the assumptions doesn't actually work. So what I want to show here is, so I just mentioned the epsilon-greedy algorithm. And so, of course, there are some documentation and so on, but you just create a class. And then here, whenever you want to select an arm, it either says, should I show the best one, or should I just show a random one? And the best one right now is the average click return. And the idea to simulate it is then, again, I say, this is the hidden distribution. So one of the arms is, it will say that it clicked on 0.2 of the time, 0.5, 0.3, and so on. And then it will run through different epsilons. So you remember I said that epsilon-greedy meant that how often it will then actually do the best one and how often it will randomize. I keep looking at this one and it doesn't work. And so let me just see if I can actually run it. How many of you managed to get into that document? How many did not manage to get into that document? Yeah. All right, good stuff. Yeah. No, I didn't share the link to the code. Did I? So did you get into the Google Doc? Okay, good. A lot of funny animals looking at it right now. So the idea with this one is that there should have been yet another tab here that will then show, that should show the, these nice drawings that you see in the next slide. I'm sorry, it's the first time for me to do an interactive tutorial. There will be a questionnaire afterwards. So there should have been the piece of code that would show these graphs. So the idea that I would like you to do now is that since we have, oh wait, no, I'm not, I got confused now. So okay, so I show you that there was an environment. Now I'm confused and not you. The idea that I actually wanted to, yeah, okay, so here is some different epsilon-greedy. Okay, sorry, I need to get back in where I was. Okay, so if you run the code that I just showed you, then there are some different epsilons. And then you can then see the regret over 1,000 iterations. And again, the regret was, does anybody know what the regret was? Guy that is running out now? Okay, so regret is how much you lost from the maximum. The idea is that what we want to do is, of course, we want to reduce the regret. But the question is, again, what should be the horizon of it? Should we take one that goes down fast with the epsilon, and then it knows what it should do very fast? Or what should we do? Because then it depends on, if you just look at the very small here, the small difference, then you can see the orange is better. And actually, you also, if you have 100,000 episodes, then or trials, then you actually don't know if the blue one will then end up being the best one because others keeps growing. So there are a series of different strategies that you can do. The one that I shown you there is the one that you just called greedy, the one that takes the best one all the time. Oh, in the sense that if you take epsilon that is very small, then you will have the greedy one. On the other hand, if you have the epsilon that is so large that it is always exploring, then you have a random one. Then in the middle, you have the epsilon-greedy one. Then there is one that says it's actually a good idea to start and then really explore a lot and then go down afterwards. There are others that say that maybe that is a bit too pessimistic. And so we can say that all of them are great, and then we get disappointed as they are not, and then they go down. That means that you will explore a lot more. And here, there should be a link that works. Sorry, I got confused. Sorry about that. So the idea is now, the code that I just showed you was very simple, but one of the ways that you can look at, these functions is to see how do you optimize your regret. And I think now I actually just showed you which ones were the best ones. But so the idea is now try and open this Colab notebook, and then see if you can update the algorithm such that the regret gets better. And if you do that a second, then I'll just copy paste the piece of code that I apparently deleted back into the document so you can make these nice plots that I'm showing of. Morten is looking at me encouragingly. Is everybody okay out there? Is it an okay task? Okay, so in the notebook I just showed you a link to. There is some code now that will plot the the regret, the cumulative regret. So you can show the charts, and if you believe you have something interesting, you can then copy it into this document or copy a link to your notebook into the document. Did you finish? Did anybody finish? Yeah? Well, you could put a seed if you want. So I haven't put a seed because the idea is that it should sample, so there is a randomness also inside of it. If you want to have a more research-pointed competition, then we could say that the seed you should put is 42. So did anybody try something? It's not a trick question. I really just don't know if anybody is doing something or they're just waiting for me to continue talking again. So let's see if we can get back to these ones. At 2:10, I'll start talking again. That's in 2 minutes. Then you can one by one come up here and then you can explain what you did. All right, so I'm getting nervous. So the greedy one is good to have if your manager will always use the greedy one because he just wants to get the most out of everything. And usually they don't understand that maybe there is a learning process. The random one is the research person who wants to learn as much as possible. And it's probably not a good idea either. Then there is the epsilon-greedy, but of course you have to decide on the epsilon beforehand. And maybe at some point, if you assume that the distributions are stationary, then that's not good either. The last one, the optimistic initialization, is there because sometimes you will have just by chance that one of the arms will be lucky and get some clicks to begin with, and then that will dominate it for the rest of the time. So if you are optimistic, if you initialize it optimistic, then you ensure better that you will explore all the arms because all of them, in the sense that if you say that all of them are the maximum in the beginning, then you can almost only get disappointed. And then, so the idea is that you kind of push it to explore all of them. And then, of course, it will go down and then it will become epsilon-greedy again. Then there is the decaying epsilon-greedy, which is actually, I'm going to spoil it, is actually the one that is supposed to be the best one. Because that one explores a lot in the beginning, and then it's fast to start optimizing it. And so, if next time somebody comes and asks you, why should we use Bandits instead of A/B test, then there's actually some research that says that you can do an epsilon-greedy decaying, and then you still end up with, that you can still use your statistical methods, and then you will still end up with being sure that you don't have a false positive, but your regret over the testing period will be lower, which is kind of what we want. Should we look at the code, or are everybody satisfied with this little exercise? So, show of hands, should I just pick the decaying epsilon one and then show the code, or should I just move on? Yeah, sure. Let's see if I can find it. But yes, let me, 1 second. So here. So basically, the way that the Bandits is implemented, it's actually not inside of the Bandit. You call the select arm, then you can't see it. So you just say initial is epsilon, and then you have a decay rate, and then you just slowly go down. One of the things with this, I have some longer code there. One of the things that you should be careful with this one is that because eventually it will actually arrive at 0, and which is great again if you have stationary. distributions, but in most cases that doesn't exist. So you should be careful always to have a little bit of exploration also. But anyway, so this is...
So I've implemented the same thing that you're showing here, which is the decaying epsilon-greedy method. And I launched this simulation several times, and I observed that it's performing the best in terms of regret most of the time, but sometimes just a fixed epsilon performs better. I think that might be due to like the fact that there is an assumption on what is the initial epsilon that you're selecting and what is the decay rate, and these choices might not be optimal. So is there a way to, I guess, kind of automatically choose what the initial epsilon should be, and what, like, kind of have these parameters also be updated in an adaptive way?
So there is a function that if you know how much you expect one thing to be better than the other, then you can calculate how many samples you have to have, a little bit like the A/B test that you go out and you say, okay, so I need 100,000 data points before I can say with statisticals. Okay, so you can take those numbers basically, and then there is a formula that will then show you what the decay should be. But the problem is that there is a hyperparameter in there somewhere, and that you have to understand based on your domain and train it and so on. So one of the X's, yeah, sure.
And I know that there are some other methods to do this, like the Thompson sampling and upper confidence bound. These methods address this problem where, like, I guess, like, it's kind of like you are...
it's not that I want to spoil what you're saying, but the next two I'm talking about is Thompson sampling and UCB. And then, so basically what we should learn here is that, so this is a randomized process where there is sampling, so you can't always ensure that it's always the same if you don't set a seed. But sadly, the world seed doesn't exist. So even if you have a good choice of epsilon, then you might have to try and simulate it a couple of times before you can be sure that this is the best one or not. The second type of bandit that I wanted to talk about is the Thompson sampling. And I confuse myself because it's also called the Bayesian bandit and Thompson sampling bandit, and I sometimes interchange those ones without knowing exactly why. One of the fun things about a Bayesian bandit is that, so usually when you talk about a distribution, you have the Gaussian distribution, which is more or less the purple one here. But the Thompson sampling one uses a beta distribution, which starts out like completely random, means that if it doesn't know anything, then if you sample from that, it can be anything between 0 and 1 all the time. And then as it learns, you can then see that then it becomes kind of a wave, and then in the end, it turns into something, that similar, is close to our normal distribution. Am I saying something wrong now, Morten? Okay, good. He gave a very long and excellent presentation last week about it, so I just wanted to be sure. Again, this is very, very simple code. So basically, to do Thompson sampling, instead of doing what we did before, you just say, okay, so each of my arms is a distribution. And every time I need to decide on an arm, I just take a sample from this distribution, and then I return the one that was the maximum. And this is some examples that show, again, the different distributions. So you start with the one over here. So you start out with the flat line when there is no data at all. Then you have probably one click. Then the line goes like, I don't know if that actually works. So anyway, after a few iterations, after 200 iterations, you can then see that these distributions start to show their true nature. And then as you go along, then it becomes more and more. Is it clear to everybody what I mean when I say that you sample from a distribution? All right, so just if somebody is afraid to say, is this actually something I can point with? Is it? No? Ah, it's the microphone. Okay, I was just like finally I understood what it was. It's a microphone. Okay, never mind. Okay, so this one I can almost reach it. So when I say that it's a distribution, the red line is arm number 3. And when it looks like this, then almost every time you say, give me a number from here, then it will be around 0.55 or 0.6. While the distribution, the blue one that is kind of a wave here, is that most of the time it will just be 0.1 that comes out of the distribution, but it's much more diverse. So since the wave is kind of flowing all over the place, you don't really know what gets out of it. And the idea with the Thompson sampling is that the ones that are better, then they slowly get their distributions pushed to the right for you or this way, depending on how you're looking at it. And then, of course, it's them that are winning most of the time. Is that clear to everybody? All right. Then I thought it could be fun to then take your same notebook and then try and change those 2 lines of the bandit and then do the Bayesian sampling instead. So this is to a different notebook, but it contains the same code. It just to try and do a Bayesian one. And if you want, I can also go back to the code, and then basically you just have to paste this into the bandit instead of the epsilon-greedy part before. And so the idea with this one is, of course, that how do you say, before you kind of constricted it to stop exploring at some point, but as with the Bayesian distributions, then that should kind of be inherent in it, that it then understands that if it's unsure about things, it will still go back and forth between them. So eventually it will be the most greedy function or arm that will be there, but the point is that it will, it will be random for quite a while. And in theory, it should be, all arms should be shown at times, even if it's kind of found the best one already.
The update estimates function, I think, like we need to do some posterior calculation after we get the reward, right? I think you haven't given us that formula.
I haven't given you the framework.
For updating the distributions.
So
So we are sampling, when we choose the arm, we sample from the distribution, right? To get
yes.
But do we have to update the distribution after we get the reward?
I think it's inside of this simulation. So it should, so is it this one you are talking about? Or am I not understanding what you're saying? So basically the implementation of it, don't look now if you want to do it yourself, but, oh, as it's here. So basically what you do is that every time you ask it to select an arm, then you put in the alphas and the betas, which is part of the initialization of the bandit. And in the beginning, it's just all ones. And that's again a question whether you should initialize that in another way. Then every time you select an arm, you update your estimate whether there is a reward or not, in the sense that you plus 1 to each of these ones. And that means that next time you select the arm and you create a new distribution that you sample from every time, then the distribution gets updated. So if we go back to the slides that I was showing before, I really hope I'm better at bandits than what controlling this. So basically, when we talk about the distribution develops, then every time you call the bandit, you make the distribution using alphas and betas. And beta is just how many times you have shown it, and alpha is how many times it got a reward or it was clicked on. So the good thing is that if you did manage to implement it, then the Bayesian bandit is pretty good. The reason why it's not all the way in the bottom is because we have, it's a static environment, and if your epsilon-greedy is very fast to find the best arm, then it doesn't explore any longer, and then it just keeps, then it doesn't regret a lot. In real world, again, then the Bayesian one is probably the better one. And so the question is, again, which ones to choose. And I think I just got ahead of myself, because basically, I say, if you look at these ones, then it seems like it's the best bandit is the one that has the lowest regret. But the question is, how much do you want it to explore? Because, I say, especially with especially with everything. With a banner, for example, it might be really popular in the morning, but an hour later or in the afternoon, it might not be so popular, or the other way around. So in many of these scenarios, you really want them to explore as much as, not as much as possible, but you don't want them to stop exploring at least. And then that was what I spoiled before, that there is actually a paper from 2002 which shows that the epsilon-greedy with decay is the one that you kind of scientifically can say that this has the lowest regret. But again, this is simulated environment, so I'm a little bit, it's hard to say which ones. Yeah. So a question for you. I don't know if I actually already said it, but do you have any idea why not to take it, other than what I just said myself?
So I think the reason you might not want to use epsilon-greedy is if the distribution is not fixed.
Yes.
Of the arms. If the distribution is changing, you always want to be exploring a little bit so that you can adapt when the distribution changes.
Yes, exactly. And I think you actually already also kind of indicated the other problem, that one of the problems with epsilon-greedy is that you have to know the right value to put into it to be sure that you don't, that it doesn't exploit too fast, or it's not too greedy and so on. So it's, it sounds easy, but there is a lot of concerns that you need to consider when you use epsilon-greedy. So often people use the Thompson sampling instead. And then, I don't know if you'll just skip this exercise, but because one of the things that I often then play around with is that if you say that you have this simulated environment, then it's great that it can tell me that I thought that arm number 4 was the best one after a certain amount of trials. But if we go back to this banner where we have a problem that the banner is great in the morning and then another banner is great a little bit later, then what does then happen? And then I was going to ask you to make a chart to show that what happens. But I think maybe we'll skip that. And I had planned to make it while you were making it, so I don't actually have it. But so the problem is, again, if we go back to this one again, if you say that after 500 turns, then suddenly the best one is not the optimal any longer, then which of these ones would then actually be the better one? And the ones that had a quick decay on epsilon, that were the ones down in the bottom here, they will just keep choosing the wrong thing, basically. And so their regret will go up, while the Thompson sampling one, which even if it goes higher in the best compared to the best ones, it's more stable within changes. So let's skip that one. One of the things that before you then go home and say, I don't want to use these epsilon-greedy ones, I only want to use Thompson sampling or Bayesian Bandits, is that the fun part about it is that, I don't know if it's the great part or the bad part, but so I want to use a bandit because it also explores. And when you then have your bandit and you just keep adding to the numbers of alphas and betas, then it doesn't actually explore any longer. In a sense that you can see here that arm number 3, I don't know, number 3, that one is basically always the one that is winning. And if you then, since the first time I talked about putting this into production, I was just like, hey, let's put as much data into it as possible, because then we are sure that it knows what it's doing. But it actually turned out that then it became these spikes, and that means that basically one winner will always be the one that will be chosen, and then you don't have any exploration any longer. So if you want to go out and use the Thompson sampling, then you should be careful to have a window that it should learn in. And so the thing that you should be careful is that, of course, you want a window that is long enough that it can learn from, how to say, what it has shown people, but still short enough for it not to end up with having distributions that are kind of spikes on a desert ground. And so that, I say, even with this one that looks like you don't have to have a hyperparameter, there are also things that can get screwed up. Do you have any questions about that? Nope. All right. This is another one that is kind of, I say, a lot of people then say, okay, I understood this, but maybe it's then too difficult to actually control what happens. And then people tend to move towards the upper confident bound bandit instead of, which is called UBC. And basically the idea behind that is that you say, you have an action score, so each arm, as you've seen many times already, each arm get a score every time that you request the bandit for an arm. And then you can say there are some uncertainty behind that. And so you can say the UCB, what that does is that it says, I have the score, and then I have the uncertainty afterwards. Let me just see, I have a nice drawing, but maybe I push that ahead. So basically what that does is that it says, so the Q value here is the average. So far we have said how many times it was got a reward over how many times it was shown. And so that's the Q function here, or the value function. And then the uncertainty of that on top of that. So it basically says it's always a great opportunity to learn. So if you have something that has been shown a lot of time, then the uncertainty goes down, and then it's only its actual value that is shown. But then next to it, then you can see that the arms that are not shown very much, their uncertainty slowly goes up. And then so eventually the uncertainty plus the average reward will then end up being the highest one, and then that will be pushed in. And in this way, you kind of guarantee that things will be explored over and over again. Let me see if I just... Yeah, so basically what I was saying is that, so every time you call this one, then the mean, meaning the average reward, increases with a positive reward or decreases with no decrease if it's 0. But then over here, this the uncertainty, the overall time spent increases. So that means that if, in a sense that the thing under the fraction, that only gets bigger when it's actually shown, while the thing on top gets larger and larger every time you move along. So if something is constant underneath and something gets larger on top, then everything gets larger. And hence you have this, this functionality. And this is one of the ones that they call optimism in the face of uncertainty. Sorry, I just need to have a sip of water. And now we are arriving to 6 lines of code instead. Again, just to go quickly through it, is that you, again, every time the Bandits is asked to select an arm, you iterate through it. Then it says, what's the sum of the rewards? And then we divide that with how many times it was pulled. Then we say, what's the uncertainty, the variance of what we want to see? We calculate that, then we add them together, and we append it to the list, and then in the end we just say, which of these ones gave the maximum? And here I just for fun took I created a chart that then showed what's the uncertainty of the arms as they go along. And so, I said, I don't know if I made a chart after. Anyway, so the interesting thing here is that the one with the lowest uncertainty is then the best one. While you can see on the ones that are not very good, their uncertainty kind of climbs up, then they get shown, and then no click, and then it falls down, and then they climb up again. That's why you get these kind of hilly motions of the lines, while these ones look like they have been pretty steady all the time. And so, if you then look at the chart here, I'm not sure why I decided to put the green box on top of which one it is, but let's see if we can guess which one it is. I think maybe it's the purple one that showed, or one of the lower ones, in the sense that the problem here is that how much do you want to explore, and so it keeps exploring. Again, there is no, it's not in this one. Never mind. So the thing to remember again is, in the long run, what is it you want to obtain? Because, as I say, bandits are usually, in the ads and in the magazines and in the movies, they're always like, this is the fast choice that will get you a reward fast. But the idea is actually, they are there for the long term. I think that that's a point that I will keep repeating throughout the next, until the time I have you. So again, which of these two should then be the winner? In a sense, the Thompson sampling one is great because you have the sampling, but you risk that these distributions become a little bit difficult to control, while the UCB one is kind of controlled, but you also lose the randomness of, so in my head, a bandit should be a little bit random, and I think that's one of the problems with the UCB. But on the other hand, there is no sampling, it's more predictable, and it shows exploration. But in the end, it depends a bit on the use case. I just realized I have toothpaste here. So one of the places where this can become a problem is that if you have delayed feedback, I'm not sure if I talk about that later, so I'll just mention it now. So often what you realize as soon as you go back home and you say to your boss, let's put in bandits because Kim convinced everybody that this was the best thing since sliced bread, then they will say, okay, but our system actually doesn't actually connect so well so you can get feedback right now. And if you don't get any feedback on, in a sense, any rewards back, then the UCB is a problem, because then, since you don't have any sampling, then it will just continue being uncertain all the time. There are ways to get around it, of course, but if you have delayed feedback and you are on policy learning, then Thompson sampling is probably your best place to start. Just to recap, because so it's often shown as an octopus or something similar, and so basically what happens every time you have a bandit is that it just iterates through each of the choices. And so instead of looking at, in the end, it's kind of like a classifier for each arm that you will have. And then which method you then decide to use to attribute a value to an arm is then what makes the bandits different. So if we should just quickly recap, epsilon-greedy, you just throw a dice, and then you decide whether you want to explore, otherwise you take the greedy option all the time. If you want to do Thompson sampling, then you do, you have a distribution for each of the arms, and then you choose the max one. And then with the upper confident one, you sum the average reward, okay, and then you take you sum the average reward. Now I understand what I wrote myself. And then how confident or the uncertainty, and then you take the max of those ones. So the question is, are we finished now? Can we do better than this? Can I make even more of you fall asleep? All right. So I think we're missing a signal. We can do better. So far we've just been talking about, basically we have created a function for each of the arms that says we have a value for each arm based on a function that is based on just impressions and clicks. But we know more usually when we show something. So there is a context we can use. And in this way, we can then maybe beef up our understanding a little bit better. And also, as I say, even if we shouldn't stop exploring, then maybe we shouldn't show horror movies to children and those kind of things. So this is my introduction to contextual bandits. In case somebody had a question, because now I'm going to move away from these ones. Does anybody have a question about those before we move on? It'll be a test in the end. Oh, okay. Okay, so basically the way you can also consider it right now is that it's great to have these arms that knows how popular they are between people, but it's a non-personalized solution. And what we actually want is personalized solutions. And that's why we start talking about contextual bandits instead. There are many different types of context, since there are the user context on one hand, who am I that comes there. Then there is the request context, which could be stuff like I'm standing in park on the stage and I'm using my cellular phone or my laptop. And then there could be, inside the arm, the context of, what's the arm represents. And here I will talk about a rather old algorithm, but it's, if you understand that algorithm, then you can move on and take over the world afterwards. Maybe that's a bold one, but anyway. So if we still look at the same very simple equation as before, basically what it's saying is that, and I still call it UCB because it's just a contextual version of UCB. I'm sorry, I should have called it something else. So we still have the expected reward based on the arm and the context that you have around it, and then the uncertainty. And then here are some equations, or here it starts at least. So basically what you can say that if you have a context, then you can say that expected reward could be a linear regression function. So you have a theta that you train on each of the bandits, and then afterwards that gives you a value, but you still have your uncertainty over there, so that even if your linear regression is very good, then the uncertainty also takes care that it keeps exploring. Yeah, so this is basically what I just said. So given a context, which is x at time t, and for that arm, then you just need to come up with what's theta. And the way that they do it in LinUCB is to use something that is called rich regression. And as I said, go and read the article if you really want to understand what is happening, in the sense that you can rewrite it into that the expected value is the same, and then the uncertainty is described like that, and then you take the argmax afterwards. That's basically the LinUCB. One of the interesting things here is that, what am I showing? So yeah, again, you should remember there is a hyperparameter, because those ones always, hit you when you least expect it. So basically, what you have here again is that, so I'm sorry I keep repeating it, but these algorithms often start seeming more scary, but again, it's just, you're really just running through the arms. And in this one, it's just saying that, okay, so if there is a new arm, then we initialize a new linear regression model, and then otherwise you just iterate through them. And then, the PT here is the predicted value, which is the reward function, and then the uncertainty. And then in the end, you just take the maximum one, and then you return that one. There are some cases that it's not shown here, but at least that I've seen in production, that sometimes the two arms will have the same value here, and then you need to do some randomization. There's a question. I don't know if you're allowed, in a sense. You can shout as crazy as you want.
I'm curious, well, thanks for the presentation. I was curious how you implement this in industrial environments, because, well, in these settings, you are iterating over the observations, and each time you're updating and you have the time to compute your a posteriori optimally, and then you take the best decision. But when you're in a real life setting, and like I remember the first slide you were showing, like basically in a platform like Netflix where you're getting like a lot of views at the same time.
Yeah.
I would expect it to be harder to compute the optimal decision at each observation.
Yeah.
So how do you do the trade-off over there? Like, do you batch your observations and then you compute
you cache
the metric, or?
So basically, when you go on Netflix and you see a banner, if you then every time you reload the page, you get a new banner, then you get confused. That's the excuse. So we cache it, and then so in the end, it's how to say. Since you asked the question, this is one of the things that we are looking into making faster right now on the project that I'm working on. So yes, it can be an issue. And the more complex algorithms you have, the bigger the issue is. But if you can, I say, when I'm finished with the presentation, there is a slide with goats and questions. If I haven't answered it by then ask it again.
Sounds good. Thanks.
All right. Promise goats, no music, but goats. So in this case, the code is a little bit more complex because now we, instead of just having two numbers and a distribution, then we need to have a little bit more code. So we still need three classes now, the Bandit, simulator, and an arm. And then when I say, wait a minute, we were talking about only online stuff before. But in these algorithms, when you start talking about contextual input, it also becomes a bit difficult just to put, you don't want to put a completely stupid bandit into production. So you simulate it using what you call replay. And this part of it becomes quite, in a sense that, again, the code that does it is pretty simple. But in most cases, there will be scenarios where it actually won't work, and then more complicated things that I will also get back into later. But so before I talked about that we were out here, and it was only after we had put something ready to production that we would look at it, while now we are trying to kind of push it backwards and actually have something that is ready for action already before we put it into production. And this time I'm probably not going to ask you to code a lot, also because, so one of the things that they always teach you before you go and present in front of a lot of people is to close all your tabs just before you go on stage. And I did that, and now I don't find, I think we're here. Marcel, are you leaving already? He tried. It's also one of the things they teach you just before you start a tutorial is to learn all the names of everybody who's here. So, all right, let's not go into that. Okay, so I promised you three classes. So basically now we have an arm. So every time we have a new arm or a new action, then we create an instance of this class. And again, what it does, in a sense, now we have some more parameters. We have the alpha parameter, then the rest of it is, let me see. So you have the arm index, then you have the D, which is the number of features, and then you have this alpha that I was talking about before, which is the variable that shows how much of the uncertainty you should be worried about. In a sense that, so when you calculate UBC, then you do some dot products that I will try not to get into, and then this line here is where you calculate the average value, or it's not the average value any longer, but now it's what's the linear regression will give you back, and then again the uncertainty. So this line is, how to say, the crux of the matter. So basically what happens again, as we saw before, that whenever a bandit is called, it runs through each of the arms. You don't see the actual for loop here because that's inside the bandits. I'll show you that in a second. But then every time it updates, it then it updates the weights inside of the regression. And then if we go down here, then again in the select arm, we then say go through all the arms again, calculate the UCB, and then it says if it's better than everybody that has been there before, then use that one as the largest one. And then it has this thing in the bottom, which is, how to say, the new complication is that sometimes these values will be the same. So you should how to say, sample on ties. So you don't risk that if it's the same, then one of them will just always win because it's the first one you index through, which will be bad. Then the simulation is exactly the same as before. No, it's not. I'm lying. So basically what you do here is that now instead of just doing some, you could do some just random auto-generated material again, but what I've done here is that I have stolen some, it's wrong to say stolen, but from Columbia University, they have a small data set that they have used somewhere else, and I've just used that one too. And so basically when I simulated it, I load the data, and then I iterate through each of the lines. And basically what it does is that the user features are the first part of the data. Then I take that data, I call the bandit, I call the bandit. So here is the part of the data that is the reward. Then, yeah, select arm, I call the bandit with the data, and then Bob's your uncle, in a sense that then we go through it. If your bandit then produced the same, so I wanted to say that the difference now is that the problem with the data that we have is that we only know what happened if that specific news item was shown. Then if there is 100 different items and it's only one of them that was shown, so we only know if you got reward on that one. And so that's the if statement we have here that says we actually only use this data point if the thing that is chosen by the bandit is the same as what is logged in the data. And if that's true, then everybody's happy and we update it and so on. And then, you can iterate through the data many times. There's a whole bunch of biases that is introduced here, which is something that I'll talk a little bit about later on, but so here should be the link if you want it for now. If you want to open the notebook, because I'm going to ask you to try and change the alpha and then see what's the difference you get. It doesn't take that long to run the code. Try and open that notebook, and then I'm not asking you to change any code at all. The only thing that I'm saying you should try out, I'll take the link and then copy it into the document. Okay, I know the bottom link is the one that I wanted to share at least. And so so basically the thing that, now I lost my mouse, this is going great. So if you just take this one, make a copy of it, and then you can run the different fields until you get down to here, the simulation of the data. Don't change the number of arms because that's the number of arms that are in the data. But if you change this alpha, then you get different results. And the point is just, again, even if we say that it can learn by itself and so on, it's actually a lot of different things can happen based on that alpha.
So this LinUCB algorithm is assuming a linear relationship between the context and the reward.
Yes.
So what if I want to use a non-linear model like a neural network or a random forest?
That's coming later.
Okay.
You have to play around with the alpha first. I'm not seeing a lot of action on your laptops here, so you can also just move on. Well, the thing that I had hoped you would philosophize a little bit about is that there is always something you have to train, and that it's great that you can do it offline now, and you can show on your data that it's, how to say, you can go and show your teammates that, look, I made a simulation that works, but then there is a good chance or risk that as soon as you put it into production, then this alpha should be tweaked a bit, along with probably also other things. And so the point that I keep wanting to make is that bandits are very simple, but there are always things that you should consider. And don't ever try and use them as black boxes. Instead, try really to understand, because even if they look simple, then that usually comes back and bites you. So I have 50 slides left. Does people want to have a break? And then, is it okay if we have a break now? Or should we try and run through everything and then say we finish now? All right, let's do 25. Let's see. So either we have to hurry and finish, or otherwise you'll go to break and then come back, and then I have 10 minutes of things to say. But let's try it out. So here you go. Here's the answer to your question. So basically, the more complex the bandits are, it's not that they do something really different than the other bandits. It's just the Q function, the one that was linear regressor before, changes. Of course, the one that we have seen so far is also disjoint in the sense that if there are values that are kind of, you can learn across the methods, like, for example, I don't know, action movie banners, if two action movies, in a sense, if you have two different arms of action movies, then maybe there could also be some learning across those two arms. And that's the hybrid LinUCB. I only showed you the disjoint one. But so basically the sky is the limit. I also found a model the other day at LLM Bandit. So I would really love to see that in production, that you have 100 arms and then it just iterates through 100 arms and calls the LLM, and yeah. So basically the sky is the limit in a sense, except for production system limits. Yeah, and so basically this is, how to say, now you know about bandits. And I know that this is a bold statement, but still, in a sense, if you have these simple things in your head every time somebody says multi-arm bandit, then you can lead it back to a for loop that goes through all the arms, and then inside each of those arms, there can be some function that will either be a distribution and it will sample, or it will be a fixed or a prediction of some sorts. But remember that, because then, as I say, then next time somebody comes you and tells you this is a very complex bandit system, then you know that. So the complexity isn't actually in the bandit algorithm, it's just all the things that it breaks as soon as you let it loose. I think that's important to understand. And then back to the simulations, because what is this that I'm saying? That I'm saying that multi-arm bandits is all about online learning and so on, and then suddenly you start talking about simulation and off-policy evaluation. So the difference between what we saw with the Thompson sampling and the epsilon-greedy and so on is that you just put them in and then they would learn and then they would update themselves again. Is that a tomato, Arnie? Because then I'll...
Yeah, sorry to go back a slide, but something that, previously you were talking about was, in many ways, bandits can be seen like optimizing for uncertainty, but optimism under uncertainty. But in some cases, in production systems, some uncertainty is bad to explore, because not all uncertainty is good, right? So do you have any thoughts about, how to mitigate that production problem as well? For example, some uncertainty that happens from not enough data. Obviously, we want to explore that, but in some cases, just even getting 1 or 2 data points, we actually, oh no, don't explore that. Is there any do you have any suggestions on how to mitigate that issue?
So the problem that you are asking is that so you want a bandit that explores, but as soon as it's not, when it has the greedy or the best arm, then it should not explore any longer? Or is it just never explore?
Not exactly. So what I'm trying to say is, like, when you're dealing with an extremely large items, scale, let's say Netflix or Spotify or something like that.
Yeah.
Sometimes you might be exploring, let's say, like Spotify example, songs with random swear words for children or something.
Yeah.
And you're like, actually, you know what? Stop that.
Yeah.
Or something.
Right.
But at the same time, I still want to explore, but maybe at some point I want to be like, no, actually, that is a bad exploration. I want to, just put some brakes on that. Like, how would you suggest you do that in production?
That you filter away the possible arms.
Yeah.
In a sense, so you do it before you actually ask the bandit to decide which arm it should show. You just say you only have these arms to choose from.
So that should be done in the arm selection criteria. Is that what you're trying
Yes.
to? Okay, perfect. Thank you.
Yeah. Actually, I have a slide later. I'll run away in the break. Every question you have, I'll just pretend that, I'll answer it later and then you'll never see me again. No, that's not true. I'll try and answer everything. So the problem is that so far we have only talked of, so the three popular bandits that I talked about was what you call on-policy evaluation policies, which means that it's the same policy. Of course, you keep updating it, but it's the same policy that is in production that is learning at the same time. The problem is that if you want to say, okay, I want to take it offline and then train the model or the bandit first, then you suddenly, then the feedback loop gets skewed, because you have something that is in production that shows arms, and then the new bandit or the new shiny bandit you have, then that is showing arms too, and then it doesn't know what feedback it will get. And then you have these situations where you have the replay, as I already mentioned with LinUCB. So basically the problem is that that you have your log data, and let's say that we just have 4 items here. If you were at consequences, this is very much like the slides they had. I just didn't manage to find some nice animal pictures first. So basically you show one of the arms, and then maybe you get a click or you don't get a click. And so the problem is here, if the new bandit I need to train on, it then doesn't have any data to show it on, then what do you do? And so the way that the LinUCB got around it on Yahoo News back then was actually that they just showed random data to a small percentage of all the users, and then that way they got unbiased data. The problem here is that this is very much, in a sense, when a lot of things just starts getting thrown around. So biased data just means that a recommender system or a bandit has already had a policy that decided what to show people. And that means then suddenly that the data is biased towards that it only has shown those ones. So we only have feedback on what that thought was the old or the logging policy thought was correct. One of the ways to get around it is that you can say, okay, so you have the random bandit afterwards, in a sense, instead of just saying, I have my logging policy, then you have a random bandit, and then you just, you show random stuff to some people, and then they get feedback, and in that way you kind of get an unbiased data set out of it. If you go to your manager and say to YouTube or to Spotify or something, is it okay if I just send out random data for people just an hour, maybe, or 2, or a couple of days, or a week, or something like that? Then they usually, you try it. Come back and tell me if you survive. So the big question here is that we have some factual outcomes, which are the ones from the log data, and what we are then interested in understanding is the counterfactual ones, the ones that we haven't shown before. And there are a lot of ways of doing it, and to my best understanding, there isn't actually really a proved way of doing it right now. Because the problem is that you cannot fill out these data yourself, because if you could, then you actually don't need a bandit. So if you can create an estimator that will then estimate them using some kind of heuristic, but then you have to remember that, even if you can prove to a certain extent that it's more unbiased, then there is the bias that is inherent inside of the model instead. So it's hard and prone to bias. Another thing that you should remember is that if you want to use the data that has been logged by another model, now I'm not talking about the random stuff, I'm talking about the ones that was logged by the bandit in production. Then if I create a bandit that shows the most popular product all the time, then that will eventually be clicked more times. No, in a sense, if you put it in front of monkeys, then they will click on it sometimes. That means that if the new policy decides that it should show this most popular product, then the chances are that you will then get it correct is much higher. So there is also a bias in there. And that's why you have to do importance weighting. And basically what you do here is that you say, okay, so how important or what was the propensity of the bandit who put it in, that showed it in production over, am I doing, so it's the logging one, yeah, over the one that says how important is it now. And then that relationship is used on the reward that was in the production system. So if you say that the reward is 1, then a very popular product that has been shown a lot of times isn't as good a reward as one that is more rare. And so you push it into a more unbiased evaluation of the system. Again, you still have this problem that if you don't randomize your data, then you still don't know what you don't know. And did I say this already? Yeah. Then there are a lot of research being done right now, because this is not completely unbiased either, because of a lot of different other reasons. And there are some papers out here, so I don't know if I could, but person could spend hours on also going into detail. And there was a tutorial that took 2.5 hours at Amsterdam RecSys, and I encourage you to go and see it. It's great, but you have to see it 5 times before you understand anything. At this point, now I'm actually going to say that I'm finished with the bandits, and then move on to the part where I'm saying what are the examples that I have thought of using bandits. And so, do you have any questions?
Do you have something to say about delayed feedback or noisy feedback, or is that something that you're going to show anyway?
After the break.
Okay.
No, I don't know. Let's see if you can do it now. It could be also great if. So basically, this is my dog. I think maybe you can end up with a little bit of feeling. Okay, Kim has been talking for 2 hours now. What can I actually do with it? And so I'm considered where I work quite pro bandit, and so one of the discussions I often have is, well, should we then stop just doing A/B tests and then only do bandits? And that's not actually what I think, because when there is a new feature, your infrastructure changes or something similar, I think it's a great idea that you have an A/B test to ensure that things are tested properly. In the sense that it depends a little bit on what kind of feature you have. If you have a new recommender model, then it's also a good idea to do an A/B test. That said, the problem is always when you say that we have a winner, then there is always a bunch of losers also. And in that case, a bunch of losers is not that somebody who was kicked out of the house. Well, it depends on but there are people that the majority of the people who has been exposed to this new bandit are happy. That means that, usually that a lot of people, they actually liked what was in production already. This can be something like your new optimized model, or it can be so many other things. And so the question is, what if we actually would like to say, okay, so some of you can keep getting experience with the previous version. And then the good thing about that is that you can say, okay, but then let's keep both of them in production, and then you put them in a bandit instead, and they say, then the bandit will figure out who should see it. In a sense that then you can have a simple bandit that shows, okay, these people, they click more on this one, this segment of people, and the other one around. So to say we should not delete the A/B tests, so we should not stop using them, but there are cases where maybe it would be a good idea, depending on what it is that you are putting into production, that maybe an afterthought after you've seen the A/B test, the result of it, it could also be that you decide to put it inside of a bandit environment instead. Then I wanted to talk a little bit about applications of bandits in recommender systems. And so we talked about the banners already, and we talked about that you could show the rows and so on, and I think I already said this. So who knows about what's a 4-stage recommender? All right, there's one from YouTube who read the YouTube paper. Okay, so the 4-stage recommender it's a pipeline. So a recommender model and a recommender system is two different things. In a recommender system, you can have many different models. And so just quickly to enlighten the rest of you on my perspective of what is a 4-stage recommender, I made this drawing for my upcoming book, by the way. So you have 4 stages in your recommender system. The first one is the candidate generator, or the retrieval. And that's where you decide which candidates that you want to actually show in the end. And so when you asked before, what arms should I show? If you end up with a bandit in the end, then that's a place where you can say you don't. After the retrieval, that might be it can easily be all your products. If you're not YouTube, for example, if you are a video on demand in Belgium, then maybe most of the items can also fit into your system. Then the filtering part of it is the ones that people have watched already, or maybe for the ones that are not good for children or something similar. Then this is where I have most of the discussions, because usually people say that there is the ranking stage and then the re-ranking stage. If we split it into 2 and say one of them is the scoring phase and then the next one is ordering, then you can say you have all your recommender models that will then put a score on each of your candidates. And that can be everything. It can be, what have I written? It can be popularity, it can be based on where you are, your age or something. And then in the next phase is where you take those values and then you order them based on that. And that doesn't have to be linear. That can also be a function that takes all the values and then decides how to order it. And the reason why I always insist on this also is that people, the way you do scoring and the way you do ordering can be optimized in different ways. And so it's very important when you have these kind of conversations that you consider which of these 2 stages that you're looking at. Bandits, they could actually be used many of these places. Because, so if you go to the back here and we start here, then everything that leads up to the scoring phase is reducing stuff. And then here we are reordering stuff. So if you consider that the most optimized retrieval part of your system, that will actually take away everything. Since if you just take the 2 most, or the 1 most popular product and then show that to the system, then that's the most optimized retrieval system you can have, right? Because the pipeline is really fast and it probably gets a lot of clicks. But so you could also have a bandit on top of it that says, how diverse should it be? Can it learn a better way of doing retrieval? Another discussion that is often with recommender system is that should I show something that somebody already consumed? Some people actually like to watch Star Wars movies over and over and over again, so why not recommend them? Why just put a business rule that says that you cannot recommend something that is already been seen? That's also something a Bandit could do. Then you can say that inside the scoring part of it, one solution that I have looked at is that you have 3 different methods. You could say that it's content-based or it's popularity or something, and then you just decide which of the algorithms that it should choose right now. That reduces the computation time, but it, how to say, I don't know always how good that works. It's more fun, on the other hand, if you use the Bandit to decide on those weights. So when you have given scores to all your items, then the Bandit can then also help deciding how important each score is. I know there is a company called Issue in Copenhagen where they said that in the mornings it was better to do collaborative filtering, and in the evenings it was better to use content-based, something like that. I think in the mornings people want news, in the afternoon they want something they know already. All right, do you have any questions? This is just kind of overview, and the last couple of slides I have is about a project that I'm working on right now. All right? So we're working on something called polite banners, which is to find out a way to show banners, to make them diverse, and then ensure that we don't bore people. Because again, if you have the best banner that is clicked a lot, then it just shows it to everybody, and then the CTR is high, but we actually want people also to see new stuff. And so I think this, one of the problems, of some of the problems that we have been looking at is that we have new users, so we don't know anything about those users. We have new features, new banners that we don't have any information about, that stakeholders then want to be shown a lot. But again, we don't want horror movies for children and so on. So there is a lot of business rules that needs to be considered. Then we have a 24-hour delay on feedback. And finally, I say it's also evil to say it's slow. It's just a normal kind of system, I would say. So basically, to what is being put into production right now, it has changed a little bit since I made this slide, I have to say. But anyway, so basically what happens is that offline, it starts by creating a data folder. Because you need to start with a success, right? That's how I saw it in the beginning, because I couldn't get Airflow to work. So I said, if I can create a data folder, then I'm half finished. Then it takes content metadata, and it takes content interactions, so it can create the user profiles. That means that it says, okay, so each movie that somebody has watched is an action movie and yada, yada, yada. And then it goes through the interactions of some days of data, and then it creates a user profile from each of them. And then it puts those ones in a cache. Then we have the retrieval of the banner candidates. The banners will change pretty often, I'm told, but once a day there will be something new. And so we also retrieve those ones, and then we generate the banner profiles based on those ones. And it's a little bit with the content metadata again, so it knows that if somebody likes action movies, then it can also see that banners have action inside of it. So we have banner profiles, we have user profiles. And then we go through the replay of training the Bandit. Again, as I talked about before, we use MLflow to store this Bandit inside of it. And then at request time, there are a few things that needs to be done. And who was it that asked? This is a problem where things can very fast become slow. I agree with that. So we get the banner candidates, we look up the user, and then we say, okay, so if we don't know the user, then we will just either use bandit type that I clever enough didn't talk about today, but let's just say we use a Thompson sampling one. So we can kind of, learn about their taste and about the new products. Then in the bottom there is a LinUCB again, and that one will also kind of train the model of it. But because of the 24-hour delay in feedback, the problem with that is that if we just created the new arms in the LinUCB Bandit, then everybody would see the new arm because the uncertainty would be so high. And so what we have decided to do is that we only put new arms into the LinUCB after it had been trained on a couple of days. And then the hope is that everybody will cancel their NetScript subscription and come over to our place and look at the banners. Do you have any questions?
2 questions actually. For the first one, in your experience, is linear approximation enough in production environment? Like, does that work well? And the second one is about how do you build your feature space for your candidates? Like, do you have domain experts, like building one-hot encodings or something like that? Or do you have some training loop that relies on some other signals to build that feature space?
Yeah. Was that 2 questions? Or was it just the first one?
So is linear enough in production? And how do you build your feature space?
Yes, and we develop them all the time. Right. To start out with, it was just a one-hot encoding to be sure that we can understand what is happening. Then we have some very clever people that are working on creating embeddings, and then we would start using those ones. And if we ever get the system to run fast enough on linear regression and we feel we have a good day, then maybe on a Friday we will put in something more clever.
And follow up, how do, like, maybe this is more of a technical question and we can handle it later if you want. How do you handle migrations between embeddings? Like, you have an embedding that's working with a well-trained bandit problem, and then someone on your team like comes up with a new feature space.
Then I would
do you restart everything?
A/B testing.
So good. Thank you.
In a sense that you could also say you do something fun with, but no, I think that would be like taking 1,000 balls and throw them into the air and then expect somebody catches them.
You ask about A/B. You said after you put new embeddings, you A/B testing with the new embeddings like config, or it will be A/B testing just for embeddings. I mean, if your bandits have already some way, not ways, but config for existing embeddings, with the new embeddings, wouldn't not train it something else to work? And then how we will, what exactly will A/B test?
So I would A/B test the system with the same banners, with the old embeddings, and then have another bandit that has the new embeddings for the same banners.
Okay, thank you.
Does that make sense? Okay, so there are 15 slides here left, and the last 5 of them are pretty silly. So should we just finish up and then say that's it? Awesome. So very quick, use MLflow for logging things, in a sense that I'm not selling you MLflow, but use something to log your training, because it will, at some point, it will be a problem if you don't. Every time you call the bandit, then log as much as possible, without doing like me and then kill your system because you also try and log the embeddings after. Yeah. So of course there is limits to it, but one of the things that are important is that you often save the propensities of the winning one. But if you want to use it to train the next model, then it's also a very good idea if you know the propensities of the other arms. Remember that they want to optimize as much as possible. So it's always a good idea to say, in the sense that sometimes you can go to a training and everything looks fine, and then you realize that it's only showing one of your arms. And that can be many reasons for it, but it's always good to have a dashboard that shows how many times does it show each arm. Then one of the things that I'm also curious about is that how often does it explore, in a sense, how often, since maybe that one is the best one and it should only show that one, but all the other times, is it then only the next one that it shows, or how is the distribution of that? So how often does it show many different arms? Then one of the things that I also discuss with people is that they are saying, well, in A/B test, you test everything out, and then you can decide on what was actually the objective afterwards. I know that in research places they say that you shouldn't do that, but so if you have a multi-objective problem, then of course you can't have a bandit unless you put it inside of some linear function or some kind of function. So there is a value you can compare. So each of the two arms are the best ones. But in the end, that should also, go to your business stakeholders and make them decide whether money or exploration or what is better, or even better, just don't tell them and then do what you think is better. And so also remember that, I talked a little bit about the arms, but also remember that it's good to be sure that it's doing well, but it's also sometimes you will see that it feel like it's doing well, and then there will be a lot of other problems that are under the board. The worst thing that can happen is that you see your CTR goes up because the system is not working, so it's only showing popular stuff, and then suddenly that works better because it's that part of the day. So always be sure to say, okay, so if there is, in a sense, everybody can say when the system is doing something that it probably shouldn't, and then just put in some guardrails and say, this is a good point. I say, if this happens, then I would like to know. And then this is actually, I don't know if this is the last slide, but so does anybody not know what this is now? Probably also be more embarrassing to say. So basically what you should think about when you want to use bandits is that think about when you want to exploit and when you want to explore. You shouldn't always show horror movies to children and the other way around, of course. Then also in the choice of bandits, should you choose something stochastic or should you use something uncertainty based, something like the samples like the Thompson or something like the UCB? And then whether you actually need the contextual part of it. Because while it's cool to have the contextual part of it, it can also make things a lot more complicated. So the next time you think about an A/B test or one, and anyway, ChatGPT generated that, and I was like, okay, I will put it on. I just can't make myself say it. Anyway, really consider what you're doing. Are you doing predictions or are you trying to make decisions? And try to think about it. Since most of the problems we have in this world, and especially in ML systems, is that people are not thinking about what they're doing. So think about it. And then I'll just say, if you want to learn more about this, then I have these suggestions. The Bandit algorithm book is very, very thin, and it's excellent to read. You can read it quite fast. And it kind of goes through the same things that motions that I've gone through today, but it's still very interesting. The Experimentation for Engineers is a great book. He really pulls it apart and makes it nice and easy to understand. And when you read those ones and you have notes in all of them, then you can move on to Bandit algorithms, which is also a great book, but it's a bit more, it requires a little bit more effort. And then, as I started saying, that the idea with this tutorial was actually to prepare as many people as possible for consequences. They gave their consequences workshop on Monday, but they have also shared the slides for their workshop. And so especially the ones with the bias of the off-policy problems and so on, it's some very good slides to look through. And then the goats and questions. I didn't answer your question then.
It's
a new
another
question.
one, sorry. How do you deal with data freshness in practical examples? Like, how do you decide when to look back at, examples of users who clicked or did not click?
Yeah.
Or do you usually consider just a long horizon?
So you're asking how much data I use to
update your belief?
As much as my system will let me do. in a sense that it depends a lot. In news, for example, if your arms are only alive 12 hours, so it doesn't really make sense to spend more. In video, it can be a year. So it depends a lot on also on the certainty you want to put into your system. I think one of the concerns in that way is also how different is it what you have in production and what it is that you want to put in production, because I say the difference is, say, the counterfactual problems you have gets larger the more diverse they are.
Okay, and last question, and I'll go out after this. How do you deal with very sparse signals? Because like we were talking about click-throughs, the click-through rates, but what if we're looking at a very rare event, like someone reacting to a marketing campaign and buying actually the product? How is there like a trick in that direction?
In a sense that no. In a sense, then do very contextual, try to know as much as possible, and then just replay a lot of times and hope that your bandit picks up on a signal.
So first, thanks for the talk, and apologize for grabbing a coffee, but I feel unfortunately this conference coffee is making me sleepy again, which actually is not the case for your slides, so thanks again. One question, you showed this practical example of where you are applying this in your current work. In the practical bandits tutorial, we of course have also talked about applying this to rankings.
Yeah.
Are you considering applying this to rankings? Any thoughts on like the practical ramifications there?
The first question is whether I consider it, and my answer is that when you got a new hammer, then everything looks like a nail. So the second question is, it's a little bit the same as a banner, in the sense, in the end, which row should you put first? Then you can either say that you just run it through once and then you just order it based on that propensity and then you hope that works. Or you can say that every time you have a new item in your list, you do a new bandit sample, taking the first arm out. Maybe that works.
Thanks for the session.
Thank you.
So my main question is, can you have too many bandits in a system? Let's say that you have one for ranking, you have one for ad placements, or you showed one slide where you can have like bandits in multiple places.
Yeah.
I guess sometimes they will actually compete like against each other and therefore increasing the uncertainty. Have you faced that problem?
No, because nobody allows me to put that many bandits into production.
Yeah, okay.
But yes, of course there is a problem there. And when you, I said, that's where it may be worse to do an A/B test. So you say that, I say, even if you have other bandits, but every time you add something new, then try and see how the relationships are in two separate variants. And there is data overflow and leakage and so on that will also be a problem there. But I don't think that there is a good answer to your question. I think that Justin Basilico from Netflix, he gave a presentation last year and he said there was something like 10 or 12 bandits on the landing page of Netflix. And how they do it is a good question.
Yeah.
That's how I was feeling when I was finishing my slides. If I actually arrived here, then funny story, since I have you, when I went here, I was kind of prepared for it, and I found my slot was the last slot, and I was like, okay, they reduced. I asked for 2 hours, they only gave me 90 minutes. I was like, okay, great, then I have less thing to prepare. Then what was it? Morten on Monday, he was like, Kim, have you noticed that that there is also? So I'm sorry if some of the things were a little bit unstructured. That's just what to say, because I had actually prepared for a lot less time. But I hope you had fun, everybody. I hope that you enjoyed the task, and I hope that you'll come back next time I do it, or something. Come back to RecSys next year. I promise not to do it again then.